All right. Well, today we will actually just look at the applications of Stokes Law. And one of the applications that we are going to work on is applications to porous media. So after this PowerPoint overview of applications, we will actually start working on the porous media portion of this course. And in that portion, we will actually figure out and prove Harman-Kozeny equation that you have mentioned in petrophysics, as well as some alternatives. And actually, we will start with alternatives, but by now we have the tools that enable us to do so. So let's get going. Basically, this is the streamline solution for creeping flow around the sphere. We got our VR and V theta velocities in spherical coordinate system. Okay? And basically, they depend on both r and theta, so I can't simplify that further, and that was the cause of all of the trouble for reaching into streamline solutions as a toolbox, because we could not simplify this flow to, for instance, just v theta being non-zero and depending on only one other variable, for instance, r. Since we don't have such a situation, then it's extremely hard to simplify Navier-Stokes or Stokes equation to something, to an ordinary differential equation that we can solve. So that's basically the fact that VR and V theta are coupled and both depend on r and theta is the reason why we went to stream function solutions to begin with. Vphi is 0, so this is a symmetric flow, so this is essentially a two-dimensional flow, and also after we went through the whole stream function solution and found VR and V theta, we can then plug it back into Stokes equation and find pressure. Okay? So this is the solution. We have the formulas. You will get to plot this solution for homework. So basically, now we actually want to know, or we went through the basic steps of the computation of what is the total force exerted on the sphere by this fluid flowing around. And we basically needed to integrate both normal and shear stress contribution. So basically we are in spherical coordinate system, and I have three coordinates. Okay? There is a radial coordinate that is orthogonal to the sphere surface, so that's what I refer to as normal onto that solid surface. And I have two tangential one in theta and one in phi direction. Phi direction is easy because we don't have Vphi, so a lot of that will be 0, but nevertheless there's still quite a bit of work in doing the integration, and the details of that you will do for your homework. But essentially we found that ultimately, this force, okay, is the resulting force is in the direction of my v infinity velocity, the velocity away from the sphere. Okay? And so this is my delta z, that's my direction delta z. And I have three components. What is this first one? 4/3 buoyancy. So that's buoyancy, right? You know that basically, is that high school or middle school? That's introduced somewhere early in physics. Archimedes' law, right? If you get yourself into a bathtub, there will be equivalent volume of fluid going up. All right. So that is my buoyant force, and that comes from basically integrating the gravity or hydrostatic portion of the pressure. So in pressure, I have the hydrostatic portion. Here, I have the hydrostatic portion. And then there I have this portion, which is basically my flow disturbance of pressure. This is the reaction to the flow around the sphere because my velocity and pressures are coupled. So if I call this hydrostatic and this flow disturbance, then by integrating the flow, the hydrostatic portion, I will get the buoyant force. And then the second portion of it is basically this what we call form drag, and that you get by integrating this second portion of the pressure, which I refer to as flow disturbance. Okay, so that's something because of the sphere form, if you will. And then the final portion we get by integrating. So both of these portions were essentially by integrating the normal component, tau r component on the, or PRR rather, both tau RR and pressure components onto the sphere. And friction drag I get if I basically integrate the shear stress on the surface. In our case, the shear stress is tau r theta. Tau r phi we don't have to look at because v phi component is 0, so it zeros out. Okay? So basically, those are all of the contributions to the force, and this portion 6p mu r v infinity, which is the drag force, combined drag force, we refer to as Stokes formula. Okay, so one thing is, okay, well, what is the range of validity of this formula? And the range of validity is essentially rather small. It's for Reynolds numbers less than 0.1. Okay, so those are the Reynolds numbers where I actually ensure that I have laminar flow around the sphere. As I get to larger Reynolds numbers, there will be small eddies ahead and behind the sphere that will basically disturb the flow. Colloidal size particles, so my Reynolds number is rho u diameter of the sphere divided by mu. And for colloidal size particles where diameters are in microns, okay, 10 to the minus 6 meters, that will often be the case. So this is one natural application for this formula. If I go to sandstone, sandstone's typical grain sizes are going to be 100 to 500 microns across. So I am in micron range. If my piece of my sandstone chips off, it's going to chip off in the sizes that are sort of multiples of these individual grains. So those are often, so in sand production, for instance, from a weakly consolidated sandstone, this formula is applicable to use on the pieces of the formation that chip off and flow with the flow. Now, is my flow during the sand production in Reynolds numbers that is less than 1? Most likely not, but then we actually need a modification. So for larger Reynolds numbers, we're actually going to show the modifications. We need the concept of so-called friction factors that sort of average any kind of turbulence that might be resulting from the flow at large Reynolds numbers, and that's coming up after our porous media applications. Okay, so this is my Stokes formula. Now, if I want, there's actually in BSL in 4.2, you can actually find, if you use the formula in the range of Reynolds numbers between 0.1 and 1, this is the applicable extension, and you can see how for very small Reynolds numbers all of this can be neglected, and I'm back down to. So this formula asymptotically goes to Stokes if a Reynolds number is approaching 0. Okay. Now let's just go over some uses of this formula. So one actually very famous application of the formula was for finding elementary charge E. So Millikan and Fletcher in 1902, they basically took oil particles and put them in uniform electric field. In uniform electric field, they exhibit both electric forces and gravity forces, right? So basically, they knew the viscosity around those little spheres, so they were able to, by balance of forces that are applied in this case, they were able to calculate what is the elementary charge of an electron. Okay? So that's quite a famous application. In subsurface engineering, especially environmental engineering, soil particle and size analysis is something that you have seen much more likely than the previous application. So basically, the speed or velocities with which particles will settle out of a liquid, okay, depends on their size. So typically, you use sieve to separate particles in different sizes. You stir the rest, and basically, based on the times of the settlement, you can figure out the portion of your soil that is in, well, these you typically sieve out, but typically you measure sand, silt, and clay. Okay? So basically you can figure out that your soil is 20% sand, 30% silt, and the rest clay or something of that form, and that is something to use for quality of soil. So sand will settle out on the order of seconds, silt on the order of hours, and clay basically stays in suspension because particles are small enough to actually stay suspended. Okay. In sand production, there's actually work here, and this is possible. There is probably even follow-up papers. This is work from Dr. Sharma's group, where Somnath Mondal, who graduated a couple of years ago, he essentially designed a number of sand screens, okay, based on simulating particles, and this is DEM, so-called DEM method, which looks at the particle-particle interaction, and also adds, so what he did is he worked out addition of the fluid forces on this, into this behavior, and that basically enabled him to see which designs will actually effectively bridge across these gaps so you can actually prevent sand from being produced into the wellbore. Okay? So you don't want to produce formation, you want to produce the fluids. Okay? So sand screens are often used to prevent, and again, you can do analysis of this screen using simulation, and that simulation effectively has Stokes' formula in there. Okay? This is from my research group. Marianne Mirabov-Lasemi actually worked out, this is the Journal of Hydrology, how to simulate straining of larger particles in a porous medium. This is quite an involved simulation that also has that DEM method, but also it has a microtomography image of a sand pack in there, and basically the particles react, they communicate between themselves and exchange forces as well as with the formation itself. And there is addition again of Stokes, or variation of the Stokes formula for the appropriate Reynolds number in there to add those forces by the fluid. Okay. So also in permeability estimates, this is our next exercise in this course. Okay. Basically, we will use Stokes flow estimate for permeability of granular media. But before we get there, just in case you're not in petrophysics class, I will introduce fundamentals of permeability. Okay? So as we know, in soil and rock, in rocks, if I zoom in, take a sample, and this is what X-ray vision enables me to do, I can see individual, this is Berea sandstone, and this is about 1.25 millimeters on the side. I can see individual grains, okay? And they're actually stuck together with, they're basically mortared together by cement in sandstone, and basically my flow happens in the rest of this, these white regions. Okay? So basically I need a model or approximate model of how well does this medium transmit fluids. Now typically, if I actually go down onto this pore scale in between individual grains, then my Navier-Stokes equation is valid for single-phase flow. Okay? But that is too complicated to actually compute that for all of the possible geometries that I might have. I can actually tell you that basically if you have about 500 by 500 by 500 numerical cells for this medium, how well you will discretize depends on how well you imaged it or how well you approximated it. If it's a sphere pack, it's going to take you 8 hours with parallel computer. Things are actually available out of the box these days. You can actually go to software that will do that for you, so you don't have to develop the software from scratch. But it's not a trivial number of hours involved. It's going to improve as we go, but regardless, if you actually want to simulate something on the reservoir level, which is where our interest is, we would like something that works in terms of approximate properties of this medium And one of them is porosity, for instance, of the medium. So those are certain measurements that we can actually do with that. And another one is permeability, which is basically ability of the medium to transmit fluids. And we typically either resort to formulas. So I measure porosity and I calculate my permeability based on that porosity and grain size. Okay. Those are some of the formulas that we will derive and that you actually learned about in petrophysics. Or you can simply do experimental measurements and have a library of your porosities and permeabilities for different media. And then what you will simulate on reservoir level is the variation of Darcy's law, where basically you have a gradient of generalized pressure, permeability, which is ability of the porous medium to transmit fluids, and viscosity of the fluid. So you can see a built-in assumption into this. This is a model. It's not always true. And there's a built-in assumption that permeability and viscosity of fluids are independent. They're not. So technically, the permeability that I measure depends on the fluid that I use, but we typically do corrections for that, and in any kind of modeling, we assume that they can be decoupled. Okay. So those are simplifying assumptions. So this is my reservoir scale, and of course, I could also have, this is for single-phase flow, but I could have the same done for multi-phase flow, in which case I need a relative permeability. Okay. What Darcy really did, and probably he would be really surprised what are all the places that we use his equations for today. But what he did is simple experiments in sand packs. Okay? And he had this flow column. Okay? It was about 1.71 meters long, so that's about here, and 1.76. So essentially a rather large column. He measured pressure at both ends, and he literally measured the volumes coming out. He knew what were the characteristics of the sand coming in, and also what is the diameter. And he found basically a linear correlation between the flux and the gradient in pressure driving this flow. This is literally the data that he used for different fluxes. So basically that, fitting those results, basically motivated definition of permeability. Yeah. Now in a more general case, and this is something that Darcy didn't do, but those are the generalizations later, okay, you could actually have this, I apologize, let me fix it right now. Okay, 3D general formulation would actually have a permeability tensor. So we are typically assuming so-called isotropic media that behave the same in all of the directions. That might not necessarily be the case. Often when we have anything with a larger content of clay, we will have alignment of the particles. So basically I will have, for instance, much longer structures in one direction and shorter in the other, so that will cause different permeability in different directions. So in most general case, you could actually measure a permeability tensor. In practice, even if I can measure this, okay, it's going to be rather difficult to simulate using a full tensor like this. So in practice, at most, what's done is that you will take a coarse sample orthogonal to bedding and parallel to bedding, because that's where you expect differences in permeability, and you would take those into account. Okay. So basically, like the most other linear laws, it's intuitive law. Basically, if I don't have pressure gradient, I will not have flow, and my flux is actually proportional to the pressure gradient. So this is the most simple law we could actually have. Now, as you actually go into larger discharge rates and larger pressure gradients, you might actually have onset of turbulence in some of the flows. So there's a built-in assumption in Darcy's law that you actually have laminar flow. So if you don't have laminar flow, then you actually have to either know that you're working with an oversimplification that might not be as accurate, or actually use corrections to the Darcy's law that are present for different flow rates. And we're actually going to mention some of those corrections together with those friction factors and the chapter that is coming up after this topic. Okay, so overall, the simplification says that this permeability embodies any kind of geometry-related alterations to the flow that I might actually have. Okay. And after that, I don't consider the details. This is work separate from Darcy, but basically you can find online Whittaker's 1984 or so proof that you can actually derive Darcy's law from pore scale Navier-Stokes equation applied to a periodic sphere packing of equal spheres. Okay. So basically, it's more than just phenomenological. It's, again, I mentioned that at the very beginning of the class. When you actually have something that was experimentally measured that's just postulated as a law, and then you also have a separate theoretical proof, which if you separately derive it from Navier-Stokes equation from the pore scale considerations, then it's really that much stronger result, and basically what you observed experimentally really captured something essential. So our outline is going to be as follows. We will now move to flow, so-called flow plus submerged objects. So basically our solution of the flow around the sphere will be one such submerged object. And we will just look at now what happens or how do I adjust it if I have multiple spheres. Okay? So basically that will give us one version of Kozeny-Kármán equation. Also, we will look at just flow through conduits that might have constant cross-section. Okay? And in this case, we will look at the fractures, tubes, and some irregular shapes that you might find that are not necessarily, so maybe a triangle or something of that sort. And you will actually get a chance to do a solution for the flow in such constant cross-section, again using a MATLAB toolbox. Okay, so, So this is just the micrograph of Fontainebleau sandstone at 100 microns, so you can see these submerged objects and how flow through a medium like this can be actually looked at flow around these objects, which are individual grains. Now, we will actually simplify those grains to be spheres, because that's where we have some hope of an analytical solution. So we will look at both dilute suspensions of spheres, where spheres are basically not really interacting with each other, and that's a very simple generalization of Stokes' formula, as well as these concentrated spheres. In this case, since spheres are so close to each other, there's no way that flow around this sphere is not affected by flow around this one, the neighboring one. Right? And we will stretch our solution to actually somehow fit into this definition and basically depend on the porosity of this sphere pack. It's going to be an interesting exercise, and this is called so-called unit cell approach. Okay? So I will ultimately fit a whole bunch of spheres together, and I will look at the balance of forces again and the total drag per unit volume of these spheres, and that will essentially give me a formula for permeability of this medium. Okay. So we will define a unit cell. Actually, I will now start writing. So my unit cell approach will assume sphere like this. Okay? So I will assume that I have sphere of radius A, and I'm going to fit it into a slightly larger sphere of radius b, and I will assume that within that sphere b, I see flow and I don't see any other spheres outside me. Okay, so that's going to be stretch of reality, but it's going to be useful in deriving a formula. And we will actually relate, well, how many or how large of a sphere B can I fit into the medium? I will relate that to porosity of the medium. And that's where this upscaling in terms of porosity will actually come in. So let's actually start writing that. It's going to be much easier. Sketchbook. So my title is Flow, Past, Submerged Objects. And by that I mean a suspension of spheres. So I have a sphere packing. And I'm going to, so each sphere is radius A. And I'm going to fit it into and I'm going to call this unit cell radius. So I'm going to try to fit as many of spheres like this that I can into my sphere packing. Okay? So I assume I have a sphere packing of spheres with radius A. How many unit cells can I fit into this sphere? Now I know that my volume of the solid, okay, is simply 4/3 h to the cube p, and volume of my unit cell is, what is my volume of the unit cell? B cubed pi. Okay? So basically, if I look at the ratio of the solid over the unit cell, it's essentially what? Okay. What is that in terms of the, so now I assume I have a lot of these unit cells as tightly packed into my sphere pack as I possibly can. What is this in terms of porosity of that packing?
P over 1 minus V.
1 minus V, right? So if V is porosity, which is the void fraction, then this is 1 minus V. unit cells tightly tightly pack the sphere packing. Some bad English there. Unit cells tightly pack, fit.
Are you assuming there's only one sphere in the unit cell?
Yes, it takes some bending, right? Because these are spheres. How do I fit spheres into spheres without having anything on the edges? So these are, bend your minds. These are tightly fit. So this is not a precise packing that I can do geometrically.
Why don't you just do, why don't you just have a cubic unit cell?
Huh?
Why don't you just have a cubic?
Because then I'm messing up with my spherical coordinates and I'm solving the problem. I need the spherical boundaries for solving the problem. Okay? So basically, R is equal to A and R is equal to B are very cool boundaries in spherical coordinates. So yes, there is some error in this, but let's say that this error is of secondary importance. It's not the overwhelming. Okay? So yes, some bending, some, should I say, mind bending required.
What does that mean?
That means that I cannot precisely pack things. Again, I would be able, if I had a sphere packing, I would be able to pack small cubes really neatly. How am I going to pack spheres without having extra volume, right?
Yeah, but if you solve this problem, you can translate it to a cube with full porosity.
Yes, but if I'm using this, that means that my sphere packing is completely packed with these unit cells, but they're spherical. Okay. So there's some extra space there. But I'm bending it to fit it in. This is just to give me approximate relationship to porosity, really. And it's not the only crime I'm gonna do here, okay? so this is far from the only crime. So I will actually refer to this as gamma. So basically my gamma cube is 1 minus V. So let's say, who has the phone or anything available, can you compute if I have porosity of 0.9 and porosity of 0.5, what should be my B in terms of A? Or B over A? Who has the calculator? Or phone? Or both? Or computer? We have all kinds of calculating devices. Come on. In which case? A over B or B over A? So can I get B over A just to kind of have a better visualization of how much bigger is B compared to A?
2.15.
And in case of 0.5? Okay. So it's not much bigger, right, this B, especially in this range of more realistic porosity of 0.5. But again, I'm still trying to fit things in. And my assumption is that this boundary assumed to be a frictionless boundary, and outside of it flow, or the rest of the packing, the rest of the flow is not disturbed by the sphere inside, which is a stretch again as well. But we will compute this nevertheless, despite of the stretches to the reality we are doing, and we will actually compare how does the formula do, and it's going to still turn out to be capturing something essential and useful. So again, outside of this radius B, I'm assuming that nobody outside sees the sphere inside, right? In terms of the flow disturbance, which is stretch of the reality. Okay. Okay. So we will assume our sphere, and we are again going to work in spherical coordinates. So basically I have phi, this meaning the angle, not porosity, theta and r, and just like we had before, we will have symmetrical flow. Okay, so spherical coordinates phi, r, and theta. Just a quick sketch. So this is my r. The theta is the angle here. And the phi is in x, y, z. So this is my angle phi. I'm going to write it using different version of phi. So there are two ways to have phi in written. So just to differentiate from porosity. So we will again assume symmetricity and no dependence on phi, just like with the in our creeping flow around the sphere. And the only thing that we will really change is we will change boundary conditions, which will change our ultimate result. Okay? So this is going to be very similar to the flow around the sphere, just with changed boundary conditions. So what are those boundary conditions? So I'm just going to make that statement. So the similar streamline approach works here as for flow around a single sphere, but with changed boundary conditions. And technically, so there are certain expectations that I have that will help me check that the solution that I get is good. I also expect as my B goes to infinity, so I have only one sphere in this unit cell, that the solution that I get here should approach the solution that I got when I had only one sphere. So that's one check that I can do later. So Control open, save. So it's a very good idea to actually set certain expectations, because as you go along, you kind of bend reality a little and make assumptions that are simplifying assumptions, but you don't want to overdo it. And these checks of what should hold true helps you actually stay within reasonable limits. So essentially, I expect that solution we get here as b goes to infinity reduces to the solution for flow around single sphere. Yeah. So I will actually now, so I have flow around this sphere, and I'm actually going to change, instead of V infinity, we will use U is V infinity. That is fluid velocity away from the sphere. And the reason why I'm using A, B, and U, I'm actually following, so details and notation are from textbook Happel and Brenner, low Reynolds number hydrodynamics. So I'm using their notation. Okay, so what are my boundary conditions? I will also attach myself to the center of the sphere. Okay? So I will be able to look at this problem from both fluid falling, because ultimately we will do balance of the sphere packing falling in the fluid. Okay? So basically you can either look at the, oh, my sphere is falling with the velocity u in the fluid, or my flow is flowing around the sphere, okay, with the opposite direction velocity. So my boundary conditions, first one, well, I'm gonna have to repeat them next time. So I'm gonna just stop here. So we will have 4 boundary conditions, and I'm gonna work on them next time.